Okay, so let's compute the determinant of this 3 by 3 matrix. Now remember that when I write the determinant of a 3 by 3 matrix, I don't need to write down the square brackets of the matrix as well. The set of bars will be enough. Alright, so remember the idea is that we want to get the REF and then keep track of what effect the row operations have. Well, the first row operation we may want to do is just do row 2 plus 2 row 1, which will create a 0 in at the beginning of the second row. Now, this is a row operation of the type add to a row a multiple of another row, so it has no effect on the determinant. So whatever matrix we get now, it will have the same determinant as the original. And you can check your algebra, this is what we get. Now at this point we want to do another similar operation, namely row 3 minus 2 row 1, and again this is an operation where we add to a row a multiple of another row, so again it will not have any effect on the determinant and it will give us this particular equivalent matrix. Now that I've done the first two row operations, you will notice and remember that when we compute the row echelon form of a matrix, we do this kind of row operation very often. It's probably the most commonly used row operation that we use because we're trying to create zeros, and that's what we're going to end up with, right? And the fact that this operation does not change the determinant is in fact something quite convenient, because again it allows us to go from one step to the other without having to worry. However, there are situations like in the next step where we're going to do changes which do affect the determinant. For instance, what are we going to do next? Well, you should know my preferences by now. What I'm going to do is I'm going to multiply the second row by 4 and the third by 5 so as to get the same entry in the leading position for the next step. But remember, multiplying a row by a number has the effect of multiplying the whole determinant by that number. So what I'm going to do is, first of all, I'm going to perform my operation, and it gives you this particular matrix, but then I'll have to equalize it. Remember, now this determinant is 4 times as big as the other because of the first row operation I've done, and 5 times as big as what I get after that because of the second row operation. To keep things balanced, I need therefore to divide by the 4 and the 5. Okay, so this is what I mean when I say you keep track of the row operations you're doing. So because by multiplying by 4 the determinant got multiplied by 4, I divided by 4. Because the determinant was multiplied by 5 by multiplying the third row by 5, I see there I wrote 4R2 and 5R2, and that should be 4R2 and 5R3. So I divide that one by 5. Okay. And finally, the last row operation again is an operation that doesn't really do anything, and so now I end up with the same 1 divided by 4 times 5, and now I've got my row echelon form. No need to do anything else with the matrix. All I have to do is multiply the elements on the diagonal. So I end up with 1 times 20 times -7 divided by 4 times 5. You will notice that I did not multiply together the 4 and the 5. In this case, it wouldn't have made any difference, but in other situation, actually leaving the denominator as is instead of multiplying it out may make it easier to cancel things out. At this point, of course, the 20 can easily be cancelled with the 4 times 5, and that leaves us with a determinant of -7. So as you can tell, not a very complicated procedure, even though its definition looks quite messy. Later on, we're going to see other properties of the determinant, which at the same time will tell us more about why it is important, but in some situation will also allow us to simplify even further its calculation.